So now I'll move on to a live demonstration. Unlike the previous tutorials, I'll be using a Vertex AI workbench, which carries a little bit more state than a Google Colab. We haven't released these yet, but we'll probably do shortly. That just uses a lot of billable components and orchestrates a lot of different systems in Google Cloud. So we want to get that right before we release it and people are potentially charged money. We'll then set up an environment to orchestrate these ML systems, including taking a look at a synthetic data set called TF-GNN. We'll transform that in a graph using BigQuery, run graph sampling using Tensorflow, and kick off model training through Vertex AI. So just please bear with me while I change the presentation to my Colab. No.
Keep in mind that you need to share the screen now.
Yes. Okay. Just okay. Let's see. Okay. Good. Okay, so in the talk, I talked a lot about system design architecture. And to instantiate a couple of components of the system, we'll be looking at an MLOps orchestration framework on Google Cloud called Vertex AI. And we can use this to build batch ML pipelines, executing many of the components that I mentioned in the talk. This thing that you're looking at right now is something called a Vertex AI workbench. It's a hosted Python Jupyter environment that's similar to Google Colab. And just to be explicit, I'm working on this web interface that's on my laptop, but there's a VM running somewhere on Google Cloud within a Google Cloud project that will receive instructions from this Colab and execute the code and interact with the other systems in Google Cloud. So I'll also be using what's called the TF-GNN data set, and this is a synthetic data set that's released by IBM on GitHub. And it's a simulation of a table of transactions. This table contains rows describing a transaction, and each transaction comes with a user and a merchant. So a user is presumably buying things from a merchant. Each row has a couple of more interesting properties, such as the amount of the transaction or the date and time, the payment method, if there was a chip used on a credit card, the state, city, and zip of the transaction, merchant codes, and some other things. Importantly, each transaction comes with a label that's called is_fraud, which indicates a fraudulent transaction. Typically in the real world, transactions come into banks, all the time, and at some point they are flagged either by some automated system or triggered by some sort of manual review with a customer as fraudulent, and a real-world ML system might receive a bunch of aggregated transactions. A couple of them are labeled as fraud, and you want to classify some held out set as fraud or not fraud, or at least give a risk score of fraud. And there's a lot of ML and statistical approaches to this problem, but in this tutorial, we'll focus on applying the basics of the GNNs that we covered before and build our model and our training routines with the TF-GNN graph library. And first, to do that, we'll have to transform this table from just regular rows into a graph and post some structure onto it. And there's a couple of million transactions in this data set, so it's not unreasonable that this problem could be solved on a single machine, but it's useful in this tutorial to explore how the distributed techniques that I was talking about for exceptionally large graphs can be used to solve this problem, and how some of the pipeline components fit together. So this walkthrough will first set up the local environment on our Vertex AI workbench for some interactive development. We'll initialize some GCP resources that we need, like storage buckets to hold data and code artifacts. We'll create a Vertex AI pipeline that will orchestrate a couple of operations. We'll create a BigQuery data set from a raw CSV downloaded by the Transformer data set, and this will simulate our real world, data aggregation of transactions. We'll define a BigQuery transformation that will then split the data into training, validation, and test splits. This particular data set defines transactions prior to the year of 2018 as training data. Validations set is the transactions included in 2018, and then test is all transactions after 2018. Then we'll start independent data flow pipelines for heterogeneous graph subsampling. We wrote a blog post about doing this in Apache Beam that goes into much more detail than what I covered here, and so I included the link that will eventually be surfaced. And finally, we'll execute TensorFlow model and training and write the save model to Google Cloud Storage. Again, this is going to orchestrate a lot of different cloud components that are available, so it's not feasible that everybody sets up their GCP project in 20 minutes or however long that we have. So I'll just walk through and kind of explain some of the ideas of how you could do this on your own. There's a ton of examples for each of these pieces online, and you could easily spin up your own complete ML system that does this. So first, if you're working within an Vertex AI workbench, again, like I said, there's some VM running in Google Cloud that is hosting this, and you maintain state between shutdowns. So you only have to do this once. We need to install all of the dependencies that we'll need to execute the code in this tutorial. That's Apache Beam, Google Cloud API Platform, and Google Cloud Pipeline Components. Google Cloud Pipelines Components is pretty interesting. Actually, I'll show you the Vertex AI interface. It'll make a little bit more sense. Within Vertex AI, you can have experiments where you kick off, let's say, like model training as a one-off job through their either Python SDK or through a command line terminal. But there's also these pipelines that you can use. And these pipelines are useful for, let's look at one that succeeded. Let's just look at this one. These pipelines are useful for orchestrating the different steps between a larger ML system. So the pipeline components library that we're importing here defines all of the Python primitives for creating each one of these components. And then we'll build a pipeline that will define this ML system, and then we'll push it to Google Cloud to actually run the pipeline. So once we've installed that onto our Vertex AI workbench, we can import all of the libraries that we need. Then we'll need to set up our compute environment. We'll need to set a project ID, which is like the name of the GCP project that we're using, the region where we want all our compute processes to be running on, some time stamping just so that we don't overwrite artifacts if we kick off one pipeline or another. And then we'll create some GCP buckets. So Google Cloud Storage buckets are just like a hosted file system. So we'll just create some space for us to save some data. We'll come in here and we'll download the CSV table of transactions from GitHub and then push it to cloud storage. We can then upload all of the rows into a BigQuery table, and we can inspect the rows, the data, or through a CLI command, which you can see here, or we can use the BigQuery UI. So going to the BigQuery UI, we can say this command created a table called card transaction, has this schema containing our users, cards, years, months, merchant info, zips, etc. We can even preview some of the data. So this is what it looks like. We have user 705 using card. Each user has a card index on 0 to n cards, whatever they have, the year, the date, the time, the amount. Merchants can also send users. That's why the money, that's why it's negative, the type of transactions, etc. So then we'll need to create some splits. So like I said before, 2018 is the key split of this data. So instead of iterating over the data set, we can create a SQL query for each split. Next, we'll actually want to build the graph from a BigQuery table. We'll write some SQL that will transform a splitter table of transactions into a graph, aggregating the node information and accumulating interesting features and targets from rows. And thinking about the problem, the first thing that you think about is that this data set implies a tripartite graph structure. You have users, you have merchants, and you have nodes. And so it's kind of simple to execute some SQL that says, okay, aggregate every unique user, get me all of the transactions that they have, count the number of cards, insert those as features, and account for the links between the users and transactions. You can then create links between users and merchants through these other transaction nodes. So again, we're just going to create a string that has some SQL to do all of this stuff. Then we're going to create a sampling spec. This we're going to write to disk because we're going to push this to Google Cloud Storage so that when we instantiate our Dataflow pipeline, our Dataflow workers can read the sampling spec. Again, this is just our plan for traversing and subsampling the graph. We're defining our seed nodes as transactions. So after we create these three node sets, these users, transactions, and merchants, we're going to want to start from every single transaction node and fan out to explore the graph. We'll explore the graph by going from transactions to merchants, from transactions to users, and then again from users to other transactions, and then merchants to other transactions. And so funny enough, somebody asked to visualize what a graph tensor would look like in one of the previous talks. And that this is what this does. This kind of jumps to the end of actually running this process, but it's useful to like inspect the graph structure to make sure that like the SQL that we were using to build the graph and the graph tensor that we defined downstream actually looks like something intuitive to like what I was just describing. This is a random graph tensor that's selected from the output of this procedure. And it does have a funny structure, right? Like every root node transaction does only have one single edge to another merchant or a user. But once you're standing on another merchant or user node, you can fan out to other transactions. You could further then sample even more, like from each transaction, sample more users and merchants. But because the information is aggregated so completely in the transaction node, I felt, maybe this was enough to propagate enough information to get a useful model. But if you build this on your own, feel free to try more complicated sampling plans. So what's going to happen is eventually in this notebook, we're going to write some code that's going to kick off some controller jobs that's going to talk to Apache Beam for us. Those controller jobs have some requirements or dependencies they need. Specifically, they need to be able to import the Apache Beam SDK, and they need to be able to read and write graph tensor protocol buffers. So they also need to know something about the TF-GNN library. We write a file. This is just being written to a local VM somewhere on Google Cloud called requirements.txt. And then what's going to happen is once the Dataflow manager spins up a machine, it's going to optimize our Apache Beam program, and it's going to say to all of the workers in the worker pool, please execute these lines of code. Those lines of code are going to have to know about the a couple of libraries. This is the TensorFlow GNN, the Google Cloud BigQuery. So this setup.py, what's going to happen is every time Beam says, oh, I think I can add another worker to this worker pool to make throughput higher on my processing pipeline, the first thing it will do is spin up the VM, install the dependencies, and then request work from the manager of the Dataflow job. So again, we need a graph schema for each split. The structure of the graph schema will be the same, but the location of the tables are going to be different. If you recall, we created 3 BigQuery tables, one for test, training, and eval. Sorry, training, validate, and test. So this is just what that string will look like at some point. I guess it's useful to review to remind ourselves of the graph schema. We have a couple of node sets. These are users, merchants, and transactions. The users and merchants are a bit boring. They just have a feature called number of cards, number of transactions. The merchant has number of transactions. These were just things I thought intuitively would be helpful for this problem, so I coded them up. And the transaction itself also contains a user ID and merchant. And it also has the amount, the city, state, zip, the year of the transaction, and some other ancillary things like did the user use a chip, or the what's the merchant commerce code for the transaction. And then finally, we have the is fraud label within the original graph schema, which we'll strip out as Nesselhan had demonstrated in her other models. We're going to write all of these graph schemas to Google Cloud Storage so that it's not only available on the local VM disk, but available to every single Dataflow worker or job that will be needed downstream. And then this is an implementation detail, but we'll have 3 Dataflow jobs to subsample the graph, and we'll want to customize each one for the split. This is things where things get a little complicated, but essentially, we're going to containerize our entire solution. There will be some model code that we'll look at in a little bit that actually implements the model. And we'll need to ship the model along with the environment to the machines that will run model training. This line builds that containerized environment, pushes it to a centralized location called the container registry on Google Cloud, and you're good to go from there. So this is the crux of the Vertex AI pipeline. This is another, I mean, it's graphs all the way down. It's just another computational graph where you specify each step, only at a much higher level of abstraction. We're defining jobs that will be run, and we'll wait on their completion to start the next set of jobs that will be run. So for instance, we have these BigQuery job operations. We're pointing at the original table of transactions. We're just executing those simple SQL statements that say, hey, look at the year, tell me what split it's in, and then aggregating them all into 3 different tables. Once those split tables are created, and you might think like, oh, why don't you create the graph then split? This is just a much more reliable way of doing it, because if you create the graph before you split, you'd have to look at the year of each node and prune the graph, and it just gets a little bit more complicated. It's just easier to split the table, which is what we do. And then for each split, we execute that longer SQL statement to aggregate the information to create the graph. Finally, and I haven't shown you the model yet. If we have time, I will. But there's this custom training job op. And that's going to spawn whatever kind of cluster topology that you want on Google Cloud. That could be a set of machines. It could be 20 machines. It could have whatever topology that you want to specify through this worker pool specs argument. In this case, I'm only spinning up one machine, but I'm giving it to NVIDIA GPUs. So you could use those GPUs for training through normal TensorFlow example. TensorFlow abstractions, distributed abstractions. Okay, so you define this pipeline, or this function that defines this pipeline, which we can do. And then the last thing that happens here is there's this call to compile. This compile call, it takes this pipeline and creates a JSON or an intermediate representation. It doesn't have to be JSON, but in this case it is, representation of this pipeline. What you'll then do is create a Vertex AI pipeline object that will look at that template file, pass the parameters that you want for your particular job, which is how you would in the real world if you were getting dumps of transaction data, maybe they're data tables, you would give it the right date and table name to look at, and then you can run the job. So what I just did is I hit enter and all of these things happened. We created our SQL statements, we created our pipeline, we compiled the pipeline, and then we instantiated the pipeline with some locations of data, and a whole bunch of jobs were kicked off. Trying to zoom in enough for the audience. That should be okay. These jobs will take some time to provision. Yes. Oh, it's not easy. Okay, well, let's just look at one component of the pipeline. So right now, this is submitting a job to BigQuery with all of these different parameters that we've filled out. and it's waiting for the machines in BigQuery to provision. At some point, we'll be able to look at the progress of the pipeline and the different tables that it makes. We'll let this run and come back to that. I also have some screenshots so that we don't have to wait. And maybe this is a better view if I can zoom in because it's static. Seems like I can't zoom in. So this was just a picture of what I was looking at, but you can go back to the Vertex AI and Dataflow UI to navigate and inspect how these jobs are doing while they're running. Again, there's 3 BigQuery jobs that create the table splits. Then there's 3 more BigQuery jobs to create the graph from each split. And then there's a custom training job that will ingest these tables and create a TF-GNN model, which will then be saved on Google Cloud Storage. This was the main driver program that we looked at live just a second ago that we're waiting to spin up. But eventually you'll get those tables will be created, the graphs will be created, and you'll be able to run the data flow sampling pipeline like I outlined in the slides. And once you do that, you'll be able to see within the data flow interface all of the operations that are being executed in a distributed manner within data flow. So the top row would be the unigraph kind of component that we talked about. Each one of those things are reading from BigQuery these potentially huge collections of nodes and features. So like the IDs and the number of transactions, the transaction cities, and all of that stuff, and also reading all of the edges that we defined in our BigQuery step. So that's the merchant to transaction edge set, et cetera. Once the data flow jobs spin up, let's check if that happened. We're still creating. So we're still creating tables, but this is useful. So we can see the main job, or we can see the BigQuery job. So this was the SQL statement that I created through the Python interface. And then let's see if there's a table yet. And this created the split table. So we know that's doing something. And we can see that the dependent steps of this batch pipeline. At some point, the data flow jobs will start, and we'll be able to monitor how it scales to hundreds or thousands of machines as it sees fit. So I only have 5 minutes left, so I'm going to review some of the node classification code that's going to be run by the downstream sampler once these jobs finish. This is written locally on the VM that I'm working on in the Vertex AI workbench. Again, we had to containerize it, so we have a Docker file which tells which defines the environment of the training job. We'll start from a base image that's publicly distributed. We copy our training code to the environment. We install Tensorflow GNN, and the program that we're going to want to run eventually is just Python pointing to the trainer.py file. The trainer.py file lives here. So again, we just import the things that we need to execute this program, and we define some flags that default to some environment variables. Nesahan and Sammy spoke about how we pre-process our features. So for the sake of simplicity, I'm just going to assume that the user and merchants don't have any information associated with them because it's typically contained in the transaction information anyway. So if our node set name is a transaction, then I'm going to start creating some hashes of some of the information. So like the city, state, strings, the merchant code, the zip, any errors in the transactions, et cetera, including the user ID and the merchant ID. If I, at some point, will want to set the initial node states through the map function layer in TF-GNN Keras layers. And then to do that for the transaction, we return this concatenation of all of these embeddings. I just chose 16 dimensions for the embedding, and then which when you concatenate all of these things gives you 128 fingerprint for the transaction and then applied a projection down to 32 dimensions on top of that. So this is kind of like a little bit more custom than some of the TF-GNN examples that are in the repo, but typically you don't have to do this. You could use our runner framework to have a very low code solution to this. I define this make preprocessing model. And so this will create another Keras model that just does preprocessing. So model is kind of like misleading here, but it's a model that will be applied at the data set level prior to training. It's not a trainable model, but we're going to use this map features to preprocess the node features, that is to create, to transform from the transaction features to their hashes. And this is the magic merge batch components method that Neslihan talked about. And since this is a root classification node problem, we are starting with transactions. We'll want to read out the first node as a label. And we'll also want to remove those during training. So that's that. Making the preprocessed data set is just a couple of accounting things. We'll need to like read the files, get the graph schema, and create a tensor spec, and do a couple of more things. This is very well documented in our current examples in our repo. And then finally, we have our model function. This is very similar to our OGBN mag example in our repo. We just defined some functions to make convolutions and next state indents a little simpler to write. Again, we define an input using our graph tensor spec, we map our features, and then we do the usual graph updates procedure that we talked about in the last talk. For transaction node sets, we'll want to propagate information over the transaction user edge sets and the transaction merchant edge sets back to the original transaction with some sort of message dimension, which is a model hyperparameter. And this is a receiver tag. Maybe read more about that in the examples. Again, we'll look at the root states by reading out the first node. We'll predict if it's fraud or not just by adding a dense layer on top, and then we'll return the Keras model. Our main program then just sets all of this up for us, and then of course we use binary cross entropy to define the loss. We, define some metrics, an optimizer, we compile it, and whatever. And so all of that will happen finally in this section once the subsampling and data transformations happen. Because I'm running out of time, I'll just quickly run another workbook that uses this trainer exactly as it is to run a couple of set of steps of training on some pre-sampled data. So this again is what the data will look like, though it's not visualized, it's in text format. We can see that we have edges from merchants to transactions. We have, where are some of the nodes? We have transactions amounts in these subgraphs. And so that all looks good. This is just our usual training code that I've copied over. This, again, just makes the preprocessed data set that we've talked about. I've compiled the model, and then we can run training. This is just on one CPU on the VM that's hosting my Vertex AI workbench. So hopefully this gives you an idea of some of like the tools and ideas that we use to achieve some scale. We use a distributed framework to shard graph subsampling over a large pool of machines. We can use tools like Vertex AI on Google Cloud Dataflow to orchestrate the individual steps of a batch pipeline. And this is something that you could schedule at regular intervals or instantiate on a trigger of an event like a data dump to a new directory or a big table, and create a real world system that scales horizontally to large data sets. Yes, so thank you very much for coming, everybody. Okay. Yeah, thank you all for coming. It was great to participate in NeurIPS and on the first day, and we're looking forward to meeting all of you. I'll take your question in a minute, and we're looking forward to meeting all of you and looking forward to hearing some of your ideas. And if there's anything we can work on together, we're more than happy to help. We're also looking forward to your questions.